Am I audible and visible to all of you? Please type yes in the comment window if I am. Good
Yes,
evening.
Good evening, sir.
भाई मैं दिखाई दे रहा हूँ, सुनाई दे रहा हूँ कि नहीं तुम लोगों को? हाँ या
yes,
ना?
sir. Yes, sir. Yes, sir.
फिर से बोलो.
Yes, sir.
हाँ, अब दिखाई दे, अब सुनाई दे
Yes,
रहा
sir.
हो. चलो, गुड. So hi Aditya, Siddhant, Sarthak, Tubhya, please switch on your camera. Nishan, all of you switch on your camera. Preetam, Rajshri, Vaidehi, Tarushika, Arush, Ramya Shri, Advik. So we were doing rotational mechanics. I think we are doing rotational mechanics in this session. Yes or no?
Yes,
Yes,
sir.
sir.
है ना?
Yes, sir.
Good. चलो शुरू करते हैं, आ जाओ. And in the last class, I think we did conservation of angular momentum. Yes or no? Or we didn't start with angular momentum? What
So we
was
did not do that.
what did we do in the last class? Last,
Torque.
sorry?
Torque, sir.
We have done only torque.
Yes, sir.
Oh. Acha. I haven't taught you moment of inertia. अच्छा, ठीक है. अच्छा, दूसरे बैच में होगा वो फिर. कोई बात नहीं. चलो करते हैं फटाक से चालू. We have done how to solve problems in rotational motion. Did we do that?
No, sir.
No. ठीक है. Fair enough. So, and I hope we have done torque. I think we have done torque.
Yes, sir.
Completed everything out of it, right?
Yes, sir.
So now there is this moment of inertia. So what is this moment of inertia? All of you please pay attention. We are learning about. So we are learning about moment of inertia, right? I'll just switch all of these off. So here we are. So what is moment of inertia first of all? So the moment of inertia of a system of particles remains constant if the distribution of mass about the axis of rotation does not change. But this is what is a property of it. It does not define moment of inertia. So what we will do is we will try defining moment of inertia. So moment of inertia is, you can write it. यहाँ नहीं लिखते इसको. This is it. So moment of inertia is a property of a body which resist the change in its angular momentum. Okay. So moment of inertia is a property of a body which resists the change in its angular momentum. What does inertia does? Inertia resists the change in, as remember, if you guys remember, inertia resists the change in, we have done this in laws of motion. Inertia resists the change in linear momentum. Inertia resists the change in linear momentum and of an object, and moment of inertia resists the change in its angular momentum, right? So if I write angular momentum here, angular momentum is written as L vector. Okay. And for the time being, we are not interested in angular momentum, but I'll give you the expression for it. It is R cross linear momentum P. So P is the linear momentum. Okay. And R is the position of the center of mass. Position of the, sorry, it's position vector of the center of mass of the object with respect to the point. It is similar to what we have done in torque, right? With respect to the point about which we want to calculate angular momentum L. Okay. And of course, L is angular momentum. Okay. Now, when do we use this expression? We use this expression for angular momentum for any object about any point, right? There is one more expression for angular momentum, and that is I omega. See, I'm just writing it for the sake of writing because this term is used here. So we'll learn about it in detail. This I is called as moment of inertia. This is not impulse. Impulse ke upar there will be an arrowhead. So this is moment of inertia. Okay. Just a second. Someone is there at the door. I need to answer. So we have L is equal to I omega vector. This is moment of inertia, right? Now, recording it, yes. Now omega is angular velocity, right? So when do we use this? So this equation can be used anytime. The first one, just as R cross F in torque, right? And this is used only when axis of rotation is defined. So this expression is used only when, or is applicable only when axis of rotation is defined. Is used only when axis of rotation is defined. So first is fixed axis. Okay. Second is axis passing through center of mass, Okay. And the third one is IAOR, instantaneous axis of rotation. Right. We have already done it. So okay. So this expression is used, I omega is used only when axis of rotation is defined. Okay. I hope you all understood the basics of what is angular momentum is, and moment of inertia resists the change in this angular momentum. Okay. Now how moment of inertia is given. So if this is the axis of rotation, all of you please pay attention. If this is the axis of rotation and this is an object which is rotating on this axis. about this axis in this circular path. Okay. The mass of the object is small m, and the radius of its rotation is, radius of the circle in which it rotates is r. Okay. So this is the moment of inertia of this object I is mr square. I hope this is a point mass, right? So if this object is rotating in anti-clockwise sense, I am writing it as I is equal to mr square. Now, just a second, I'll write it below it. Now, if there is another object, let's say there is this object. Okay. And this object is rotating in this circular path. Let's say this mass is m1, this mass is, the radius is r1. And it is rotating in anti-clockwise sense, clockwise sense, sorry. So I1 is equal to m1 r1 square. Okay. Then comes another object is here. This is the third object. And it rotates in this circular path. It rotates in this circular path. Now this is, mass is m2, radius is r2. And the moment of inertia of this is I2 is equal to m2 r2 square. Now let's say we rotate it in clockwise sense only. Okay. So two of them are rotating clockwise. The third one is rotating anti-clockwise. The first one was rotating anti-clockwise, right? Now, if I ask you to write the net moment of inertia of all these three particles, what you will do is you will take any one direction as positive and the other sense of rotation as negative. So I am taking the anti-clockwise sense as positive. So it is plus I minus I1 minus I2. So what is plus I? It's mr square. What is I1? It's m1 r1 square. What is I2? It is m2 r2 square. This is capital I. I hope all of you understood it. Yes or no?
Yes, sir.
Yes,
So
sir.
this is how we use moment of inertia. Write it quickly and then we will move ahead. I will not be doing the derivations of it. I'll do one or two derivations only, but you have to watch the derivations from the recordings, right? I'll not waste my time on derivations. We will use that time in more of solving problems based on moment of inertia. Once you are done writing, just type done in the comment window. And please be quick. I hope all of you are done with this. Yes or no?
Yes.
Yes,
Okay.
sir. Yes, sir.
Now let's go back to the mind map and I'll open. See, I'm just giving you the formulas for it and it is all about the axis passing through their center of mass, right? So this is point mass. The moment of inertia is mr square. It is rotating in a circle of radius r. All of you are aware of it. Rod's moment of inertia about an axis passing through its center of mass perpendicular to the length of the rod is ml square by 12. Rectangular plate, it's ml square. ये गलत है. नहीं ठीक है. ml square by 12. Ring mr square. Disk mr square by 2. Cylinder mr square by 2. All of you write it first. Okay. Just a second. I'll close this one. हाँ. इसको लिखो पहले सब लोग जल्दी से. चलो done.
No, sir.
See, derivations is what you need to look from the Physics Pro Gold lectures. ठीक है, Physics Pro Gold or Physics Pro Live 11th standard, all is there. So you can do it. ठीक है. Shall we move ahead?
Yes, sir.
Okay. All of you write this first point also. It is of much importance to us. So write it. Once you are done, type done in the comment window. वैदेही हो गया बेटा. वैदेही, तुभ्या, तरुशिखा, स्तुति, सिद्धांत.
Yes, sir.
Yes, sir.
Okay, good.
Yes.
So, chalo, let's discuss this. I'll do one derivation for you, okay? So, moment of inertia of a ring. Now, all of you are aware about mass distributions. All of you are aware about mass distributions, right? You are aware about linear mass density. Yes or no? Tell me this. Linear mass density. Then you are aware about surface mass density or areal mass density. Okay. And the last one is volume mass density. Okay. This is represented as lambda. This is equal to mass per unit length. Okay. This is represented as sigma. This is mass per unit area. And this is represented as rho. And this is mass per unit volume. We are aware of these three densities, right? Now here, and I am discussing moment of inertias of only those objects which have a uniform mass density as of now, right? We will be doing those cases also where the density is not uniform. But here we are interested only in those objects which have uniform densities. Now, this is a ring. The mass of the ring is capital M, its radius is capital R. Mass is uniformly distributed. So here it is in the length, right? So M upon 2 pi R. All of you, yes or no? Understood or not?
Yes.
Lambda here is
Sir.
M upon 2 pi R.
Yes, sir.
Shipita?
Yes, sir.
Rangila, you take good care of yourself. Don't worry about those things. Okay?
Thank you, sir.
Be regular in the classes. Don't worry. Everything will be fine. So, this is the center of the ring. And along this axis only, about this axis only, we want to find its moment of inertia. So what we will do here is, we will take a small element here. Let's say the element is having its mass as dm. Can we write it? Yes or no?
Yes.
And the ring is rotating in this direction, in this sense of rotation, anti-clockwise sense. Sorry. The ring is rotating in clockwise sense, right? The ring is rotating in clockwise sense. Now, the radius is how much? The radius is r. The radius is how much? The radius is capital R. Now, can you write moment of inertia of this small particle about the axis of rotation? So DICM, that is center of mass, right? Can you write what is the moment of inertia of this about center of mass? Nishant Narayanan, tell me. Nishant.
dm r square.
Very good. It's dm into r square. Very good. So it's dm into r square, right? Now, when we integrate it, it's from 0 to ICM. And this dm is, since it is constant, since lambda is constant. So remember, whenever lambda is constant, right, only here mass is the variable. So you can easily integrate it as from 0 to m. If density varies, then you cannot integrate dm as it is. You have to write it as lambda into dx and then you have to integrate it. But in this case, you need not have to write it. So ICM is mr square. Integral of dm is m. When you substitute the limit, it is capital M. Write it quickly. Okay. Okay. Pay attention. All of you, please pay attention. I am explaining you the first statement which you have written at last. Okay? I am explaining you the first statement of mind map. which you wrote it at in the last, right? The moment of inertia of a system of particles remains constant if the distribution of mass about the axis of rotation does not change. Let's see how we can apply it. And this is an excellent application. You will all, and if you understand how to apply it, your many questions will be solved. So let's say this is mass capital M and it is rotating in a radius of R. This is center C, right? Now, this object is rotating in clockwise sense. What is its moment of inertia as of now? All of you tell me, what is its moment of inertia at this point in time? Any one of you? Okay, Vaidehi, tell me. Vaidehi.
Sir, mr square.
Shabash beti, very good. It's mr square. Okay. Now, all of you agree to this? The moment of inertia is mr square. Just now we have seen it, right? Now, if I break this object in two parts and the mass is m by 2 and m by 2. I can place it here. I can place it anywhere, right? So this is m by 2 now. And this is m by 2 now. The radius is r. Okay, the radius is r. What is moment of inertia about this end? This object? I1 is m by 2 r square. Yes or no? And moment of inertia of this object is also m by 2 r square. What is the net moment of inertia about this axis? It's mr square. Yes or no, all of you? Sum of I1 and I2.
Yes, sir.
Yes, sir.
Because both of them are rotating in the same direction, right?
Yes, sir. Yes, sir.
So now you break it into four parts. You break it into four parts. 2, 3, 4. Okay. This is m by 4, m by 4. Now this becomes m by 4. And this also becomes m by 4. Right. Moment of inertia of this is I3. This is m by 4 r square. This is m by 4. I3 is, sorry, I4 is m by 4 r square. So if you sum all these, again, it comes out to be I is equal to mr square. I hope all of you understood this. Yes or no?
Yes, sir.
Yes, sir.
Very
Yes.
good. So the statement is very much correct. And here you can see that in this ring, what we have done is we have just distributed the entire mass on the circular periphery of the path, right? And that is why its moment of inertia is mr square. I hope all of you understood this. Yes or no?
Yes, sir. Yes, sir.
So the moment of inertia of a system of particles does not change if the distribution of mass remains intact from the axis of rotation. This is how we justify it. I hope all of you are agreeing to it. Noted
Yes,
it? Noted
Yes.
it? Okay. So let's move to next part of it. I'll do one more derivation for you. That is moment of inertia of a disk. Moment of inertia of a disk. Okay. Now, this is a disk. Mass is capital M, radius is capital R. And we want to find its moment of inertia about an axis passing through its center perpendicular to the plane of the disk. That is axis of the disk. Now here what we are doing is we are taking a portion, a circular ring. Always choose the element. Okay, write it like this. Always choose the element. Always choose the, element the moment of inertia of the element chosen is known to us, is known. Okay, so we are aware of the moment of inertia of the element which we have chosen. So we are aware about moment of inertia of ring. We have just now found it. So here you can see that. एक second, huh? अब ठीक है. So this is small r, and this is the width of the ring is dr. All of you, please pay attention. The width of the ring is dr. Okay. And this is small r. Okay. Now, what is sigma here? Sigma is m upon pi r square 2. Sorry. M क्या किया मैंने? M upon pi r square. This is sigma, right? Mass per unit area of the disk. Sigma is m upon pi r square. What is the area of the orange color portion? Now this ring has a width, right? The ring has a width of dr. So area of the ring is 2 pi r into dr. All of you agree to this or not? Type yes or no. Say yes or no.
Yes, sir. Yes, sir.
So dm is what? Dm is sigma into dA. And this is m upon pi r square into 2 pi r dr. Now when you solve it, it's 2mr dr upon r square. This is dm. This is dm, right? Now, what is moment of inertia of this ring about the axis? It's dm into r square. So we have 2mr cube dr upon r square. This is di. Now you integrate it from 0 to I, and this capital R, small r is integrated from 0 to r. So this is I, and this is 2m upon r square into r power 4 over 4. This is from 0 to r. This is mr square by 2. Understood, all of you? Now you do the remaining moment of inertia of other continuous bodies, right? I hope all of you understood this. Yes or no?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Advik, you understood or not?
Yes, sir.
Okay. Okay. So if you are done writing it, We will do something more with it. Done?
Yes.
Yes, sir.
चलो अब देखो, again we are using the first statement. ठीक है, we are using the first statement. If you pull this ring, all of you pay attention. This is the ring which we have, right? If you pull this ring along its axis, this ring will become a hollow cylinder, yes or no?
Yes, sir.
So the moment of inertia of this ring, of this hollow cylinder about the axis, since the mass distribution around the axis remains as it is, can I say that moment of inertia of hollow cylinder is mr square, yes or no?
Yes.
Yes, sir.
Sir.
Since the distribution of mass has not changed, right? So this is how hollow cylinder is calculated. But you can again use the integration thing for that. Now this is a disk. Draw the disk. And now when you pull the disk along its axis, it's a disk, right? So it becomes a solid cylinder. So now we can easily say that solid cylinder is having the same moment of inertia as the disk about the same axis. Hello?
Yes, sir.
Yes, sir.
Understood, all of you?
Yes, sir.
Good.
Yes.
Now comes rod. Okay. So moment of inertia of a rod. About an axis passing through its center and perpendicular to its plane. Okay. Not plane. It's not plane. Sorry, my bad. Perpendicular to its length. Now pay attention, all of you. This is the rod. This is the rod. And we want to find its moment of inertia about this axis. The element which we will choose here is a small length here. Right? At a distance x from the center of the rod. This length is dx. This length is dx. Okay. Now, mass of the rod is m, length of the rod is capital L. So here length is distributed, mass is distributed over the length. So mass dm of that element dx is what? Lambda into dx. So it is m by L into dx. Yes or no, all of you?
Yes, sir.
Yes.
Now, when this rod rotates in this sense, all the particles on the rod will rotate in the same direction. Yes or no? In the same sense of rotation. Yes or no?
Yes, sir.
So moment of inertia di about the center of mass is dm into x square, and this is m by l x square dx. This is ICM. This is minus L by 2. This is minus L by 2 to plus L by 2. When you substitute it and integrate it, this is x cubed by 3 minus L by 2 to plus L by 2. So this is ml square. So this is ml square upon 12. This is ICM. I hope all of you understood this. Yes or no?
Yes, sir.
Yes, sir.
Yes.
Likho. चलो भाई चले आगे.
Yes.
When you spread this rod like this, what you are doing here is you are just, देखो इसको, you are spreading it along this length, right? It becomes what? A rectangular plate, right? This length is B, this is width, and this is length L of the rod. Sorry, L of the plate. This is breadth B. Moment of inertia about this axis is what? It remains same, ml square by 12. Yes or no? Hello?
Yes, sir.
Yes.
Similarly, moment of inertia about this axis of rotation, which is perpendicular to the breadth. This was I1, this is I2. This is mb square upon 12, right? Yes or no?
Yes, sir.
Yes, sir.
Because it becomes a rod along this length. See? है ना? So this is how we can find its moment of inertia. Any doubts till this point?
No.
Hollow sphere's moment of inertia is 2 by 3 mr square. Solid sphere's moment of inertia is 2 by 5 mr square. Clear?
Yes, sir.
Chalo. So let's start. Let's go back to the mind map. All of you noted it?
Yes.
ये लिखा कि नहीं लिखा? और सब
Yes,
अपना
sir.
अपना अपना सब कैमरा बंद करके बैठे रहो, है ना? मैं भी कल से अभी कैमरा बंद करके पढ़ाता हूँ. रुको जरा, फिर कहना इंटरेक्शन नहीं होता है. नालायकों, आरुष, आदित्य, अद्वैक, आयुषी, रंगीला, निशांत, स्तुति, तरुशिखा, तुभ्या, वैदेही, सार्थक, ओजस, लिखा कि नहीं? नोटेड और नॉट?
Yes, sir.
Yes, sir.
ओके ओके.
Yes, sir.
चलो अब लाते हैं लास्ट वाले पॉइंट पे. ठीक है, सो आई विल क्लोज ऑल दीज. The first, there are two theorems on moment of inertia. One is, the first one is parallel axis theorem. The first one is parallel axis theorem. This is valid for all the bodies, whether it is one-dimensional, two-dimensional, three-dimensional. The distance between the two parallel axes is d, and compulsorily the moment of inertia about the center of mass has to be known. We should be aware of it, right? ICM is what we are aware of. So in this case, I'll just draw it and show it to you. This is a body, right? And let's say this is the center of mass of it. Okay. I know moment of inertia of this body about an axis passing through this point. Okay. So this is ICM. Now, if you want to find moment of inertia of the same body about this axis. Now this axis is parallel to it, right? These two axes are parallel to each other. You can easily write, so suppose this is D. The mass of the object is M. So moment of inertia about this axis of rotation is ICM plus MD square. I hope all of you understood it. Yes or no?
Yes, sir.
Copy it quickly. Chalo. Now, see an example based on it, right? We have this rod here. Pay attention, all of you. Just now we have found the moment of inertia of a rod, right? So about an axis passing through its center. So this is the axis through the center, right? Mass is capital M, length is capital L. The moment of inertia about an axis passing through its center of mass perpendicular to the length is ml square upon 12. Now, if I ask you to find its moment of inertia about this axis, see,
ml square by 3.
so this is very good. So this is L by 2, right? How to use it? It's simple. ICM plus ML square by 4. So this is ML square by 3. The only most important condition is you should know the moment of inertia about an axis which is parallel to this line. See, even if you know the moment of inertia about this line, then this is ICM, right? But this line is not parallel. In this case, the purple line is not parallel to this line. So you cannot use this ICM. You can use moment of inertia of the only that axis which is parallel to the given line. I hope all of you understood this. Yes or no?
Yes.
Yes, sir.
Noted it? Noted this point?
Yeah.
Okay. So let's go to the next one. Perpendicular axis theorem. It is valid only for planar bodies. So the first one was valid. Please pay attention. The first one was valid for all the bodies. The first one was valid for all the bodies. The second one is valid only for planar bodies. Got it? So if the moment of inertia of the body is known about any two mutually perpendicular axes which are coplanar with the body, then this is how it is given. Again, if the moment of inertia of the body is known about any two mutually perpendicular coplanar axes, remember these terms, these are important. Mutually perpendicular axes which are coplanar with the body, right? you can use this perpendicular axis theorem. So I'll just draw it here. Now, suppose I know okay, draw the rectangular plate. This is a planar body. You are aware about moment of inertia about this axis passing through the center, about this axis passing through the center and perpendicular and coplanar to the body. Yes or no? All of you.
Yes.
Yes.
These two axes are perpendicular to each other and they are planar to the body, right? So x dash, y dash. You are now aware about ixx and iyy. So, moment of inertia about this axis, which is perpendicular to the body and perpendicular to these two axes and passing through their point of intersection. Let's say this is z axis. So, izz has nothing but ixx plus iyy. So, moment of inertia of this rectangular plate, which has its breadth as b and length as l, is what? I is ml square by 12 plus mb square by 12. So this is m by 12 times l square plus b square. This is I. बात समझ में आई या नहीं आई? Advik, you understood or not? Hello, Advik.
Excuse me, sir.
एक second. Advik, you understood or not? Advik.
Sir.
हाँ.
The
Understood
screen is still the previous one, sir.
Yes, sir.
now you can see.
Yes, sir. Now it came. Explain once again, sir.
हाँ. कौन कुछ पूछ रहा था अभी? एक्सक्यूज मी किसने बोला था अभी?
सर मैंने.
हाँ बोलो.
सर स्क्रीन के लिए बोला था.
चलो दिख गया ना?
Yes, sir.
All of you do it quickly, please. Write it quickly. Remember the conditions. Please remember the conditions. These are very important. Valid for all bodies. Valid for planar bodies. These are very important conditions. Please remember it. चलो. हाँ भाई. Done with it? All of you?
Yes.
Yes, sir.
Shabash. So I'll give you one example to solve. This is a cube. Pay attention. This is a cube. Okay. I want you to find its moment of inertia about this axis. About an axis passing through one of the edges of the cube. The mass of the cube is capital M. Its dimension is small a. हुआ नहीं हुआ?
Sir, 1 minute, please.
लगाओ लगाओ दिमाग लगाओ. ये तुम्हारा होमवर्क है, जाओ. एक और क्लास है मेरी अभी. हाँ गलत है सानवी. स्ट्रॉन्ग. ma²/6. आदित्य गलत है. Very simple. It's very simple. सार्थक एग्जाम बिल्कुल सही, एकदम बहुत बढ़िया. हाँ आदित्य ठीक है. Very good. So this is your homework for next class. We are meeting when? For 12th standard. See, tomorrow there is no class. Day after tomorrow there is no class. We will be meeting on Wednesday now. Probably day after tomorrow I am thinking of it. देखते हैं कल का भी देखता हूँ मैं. ठीक है, I'll update you in the chat window.
Yes, sir.
चलो bye. Take care.
Thank you.
Thank you so much. Bye.
Thank you, sir.